In 1957, a German farmer could unbolt his combine and drive away on a tractor before lunch. In 1987, a Claas was already rolling on rubber tracks, 10 years before the industry called that idea new. In 1991, a Massey Ferguson was drawing satellite yield maps while most farms still ran on paper and memory. These machines were real, they worked. Then the industry forgot them for 30 years. Here are 10 harvesters that arrived far too early. Number 10. Claas Huckepack. Let's start with the strangest machine on this list, and possibly the most modern idea of the entire 1950s. In September 1956, at the 44th DLG Agricultural Show in Hanover, Claas unveiled something that didn't fit any existing category. They called it the Huckepack, German for piggyback, and it was two machines pretending to be one. The base was an implement carrier, a self-propelled chassis with a 3-point linkage behind the drive axle, a road PTO, an independent 540 RPM PTO, and mounting points between the axles for tool carrier implements. The gearbox was a 5-speed unit with a reverser ahead of it, which meant the Huckepack could travel just as fast backwards as forwards. On top of that chassis, you bolted a complete combine harvester unit, a full threshing body that could be lifted off again when harvest was over. 2 people could make the changeover in about an hour. Think about what Claas was actually solving here. A combine in the 1950s sat idle for roughly 11 months of the year, and for a small farm that was an impossible amount of capital doing nothing. The Huckepack's answer was to make the expensive part, the engine, the transmission, the chassis, the driver's seat, work all 12 months and rent out the rest of the year to plowing, carting, and mounted implements. That is not a 1950s idea. That is the modern system carrier concept. The same logic behind every high-clearance tool carrier and every one-platform many-jobs machine you see marketed as innovation today. So why did it fail? Partly because the execution fought the concept. In combine mode, the steered axle ended up at the rear, so the driver's seat had to be swung a full 180 degrees, and once you did that, the pedals were reversed. Operators hated it. The engine, at somewhere around 25 to 27 horsepower, was simply not enough machine for either job. And then there was the price, 17,680 Deutschmarks in 1957, which was serious money for exactly the small farmer the machine was aimed at. Claas stopped production in 1960. Best estimates put total output at only around 900 machines. A rounding error next to the Claas Super, which sold over 65,000 units. The Huckepack wasn't a bad idea, it was a correct idea. Built with 1950s hydraulics, 1950s ergonomics, and 1950s power. Give those engineers a modern hydrostatic drive and a 200 horsepower engine, and they'd have built something farmers would queue for. Number 9. John Deere's Hillside Combines. Now go to the Palouse, the rolling wheat country of eastern Washington and northern Idaho. Some of the richest wheat ground in the world, sitting on slopes that reach 50% grade. Ground so steep that a normal combine doesn't just lose grain on it, it tips over. The answer was the self-leveling Hillside Combine. And while the levelers themselves are still built today, almost nobody outside the Pacific Northwest knows this technology exists or how old it is. The principle is beautiful. The wheels follow the hill, the body doesn't. A hydraulic leveling system tilts the entire threshing and cleaning body against the slope, so the sieves, the shoe, and the separator stay flat and horizontal, while the machine crabs sideways along a hillside. Because grain cleaning depends entirely on gravity and airflow, a shoe tilted 15 degrees dumps everything into one corner and throws good wheat out the back. Keep it level, and the machine cleans as if it were on a billiard table. The idea itself was not new, even in the 1950s. The first leveling harvester technology traces back to the Holt Company in California in 1891. What changed after the Second World War was automation. Instead of a driver constantly working a lever, systems appeared that sensed the machine's attitude and corrected it automatically. One of the key figures was R.A.A. Hanson, a farmer from Palouse, Washington, whose level-sensitive control system could be retrofitted to almost any combine and eventually grew into a full engineering company. Sit with that for a second. In the 1950s, on farms in Idaho, there were combine harvesters running a closed-loop automatic attitude control system. A sensor measured the error, hydraulics corrected it continuously, and the operator just drove. That is a self-leveling platform, the ancestor of every stabilized camera gimbal, every actively leveled cab, and every terrain-following implement on the market. John Deere built factory Hillside machines for decades, the 55H, later the 95H, then the Hillside versions of the 6602 and 6622. When Deere eventually stepped back from building them in-house, specialist firms in Spokane and Idaho carried the work on, and companies like Hilco still fit leveling systems to new combines today. The strange part of the story is that mainstream combine design largely walked away from leveling. Machines got wider and heavier and more stable, and rotary separators turned out to be less fussy about tilt. So the industry decided the problem had gone away. Then it came back. Manufacturers now sell slope specialist combines for European hill country and self-leveling cleaning systems on rotary machines. New Holland introduced one on a rotary combine in 2002. Every one of those is walking a path that Paulus farmers had already surveyed half a century earlier. Number 8. Rostselmash SK-4. Here's a machine that a Western audience has almost certainly never seen, and it was, for a time, the most decorated combine harvester on Earth. Rostselmash began building the SK-4 in Rostov-on-Don in February 1962. It replaced the SK-3, and the headline number was a roughly 25% increase in output over the machine it replaced. What makes the SK-4 remarkable isn't a single clever mechanism, it's the philosophy. And the philosophy was scale. The Soviet Union had a problem no Western manufacturer faced. It needed to harvest a continent in a season with machines that could be fixed in a field by a mechanic with hand tools and no dealer network within 200 kilometers. So the SK-4 was engineered around manufacturability and serviceability, simple, repairable, standardized, and produced in numbers that are genuinely difficult to comprehend. Rostselmash had already built its 100,000th self-propelled SK-3 by January 1961. By August 1969, the plant had produced its millionth harvester, and the world noticed. The SK-4 took a first-degree diploma at the International Exhibition in Leipzig in 1963. It won a medal in Czechoslovakia in 1964, and in the same year it took a silver cup in Hungary. For a period in the 1960s, this was one of the most award-laden harvesting machines anywhere. The genuinely forward-looking part was the platform strategy. Rostselmash didn't build one combine. It built one base machine and then spun off variants for different conditions, hillside versions, rice versions, machines set up for non-cereal crops. One core design, many configurations, all sharing parts. That is exactly how every major manufacturer operates today. Common platform, modular options, regional specifications. In 1962, most Western firms were still building genuinely separate machines for separate jobs. The SK-4 was replaced in 1973 by the Neva SK-5, a machine so fundamentally sound that versions of it stayed in production for decades. In the West, we remember this era through Deere, International Harvester, and Massey. Half the world's wheat was coming off behind a very different silhouette, and almost none of us can name it. Number 7. Fortschritt E512 and E516. If the SK-4 was built for scale, the East German Fortschritt machines were built to prove a point, and they did it well enough to sell into the West. The E512 came out of the VEB Mähdrescherwerk at Bischofswerda and Zingwitz in 1968, and it was the first Fortschritt combine developed entirely in East Germany rather than adapted from a Soviet design. Its predecessor, the E170 series, had been a modified Stalinets. The E512 owed nobody anything. The numbers: a 6.5 6-liter 4-cylinder diesel, producing around 105 horsepower. The same engine family used in Fortschritt tractors, which meant parts commonality across an entire national fleet. A standard header of 4.26 meters with a 5.7 meter option. A threshing drum, 1.28 meters wide. and a cab that, for 1968, was genuinely civilized. Noise levels around 85 decibels at a time when most operators were going deaf slowly and calling it work. It stayed in production until 1988. Total build, 51,412 units, making it the most produced East German combine ever. Then, in 1977, came the machine that should be far better known, the E516. This was a giant by any standard of the era, East or West. A 13-liter V8 producing something in the region of 228 horsepower, headers of 6.7 or 7.6 meters, a threshing drum up to 80 centimeters in diameter, hydraulic adjustment of the drum and the straw drum from the seat instead of spanners and guesswork, and critically, a hydrostatic drivetrain, giving fully variable ground speed from 0 to 20 kilometers an hour without the driver ever touching a gear. Hydrostatic drive on a combine matters more than it sounds. The threshing system wants a constant rotor and drum speed to work properly. Ground speed needs to change constantly as crop density changes. A hydrostatic transmission decouples the two completely, and that's why it's universal today. Fortschritt also offered options that read like a modern spec sheet, air conditioning on machines destined for export, and a mechanical automatic guidance system that used a small feeler wheel on an arm to follow the edge of the standing crop and steer the machine along it. Automatic guidance in the 1970s without a satellite in sight. These weren't Eastern Bloc curiosities sold only at home. Fortschritt combines went to France, Denmark, Sweden and Finland, and sold in respectable numbers against Western competition. The later E514 could even be ordered on crawler tracks. Then the wall came down, the market reorganized, and one of Europe's most prolific combine builders effectively disappeared from public memory in under a decade. Number 6. Sperry New Holland TR70. In 1975, New Holland put a machine on the market with a slogan painted right on the back of the prototype, "No straw walkers." For an industry that had been building straw walkers since the 19th century, that was close to heresy. The TR70 was the first production twin-rotor combine and the first New Holland combine built in the United States. Inside, instead of a transverse threshing cylinder feeding a rack of oscillating straw walkers, it had two rotors, 17 inches in diameter, mounted at an angle, which both threshed the crop and separated the grain as the material spiraled its way rearward. The physics were the whole point. Straw walkers separate grain by shaking a mat of straw and letting gravity do the work, and gravity is slow. Rotors use centrifugal force, which is dramatically stronger, and they thresh grain against grain rather than beating it against steel. The result was gentler treatment of the sample, less cracked and damaged grain, and lower losses out the back, all in a machine that was physically shorter than a Walker combine of the same capacity, because angling the rotors let the engineers fold the crop path into a smaller body. That compactness had a bonus the marketing team leaned on hard. The TR70 handled hills well, and a shorter, more balanced machine was easier to keep planted on sloping ground. Spec-refection for the enthusiasts. Buyers chose either a Ford gasoline engine of around 142 horsepower or a Caterpillar diesel of around 166. The grain tank held 158 bushels as standard and 190 with extensions, and it unloaded at 1.5 bushels per second through a fully enclosed auger that would unload at any angle. Optional air conditioning, a heater, an AM/FM radio, and a monitor system in 1975. The story after that is the interesting part. The TR75 replaced the TR70 in 1979 with a bigger TR85 alongside it. The 25,000th TR rolled out in 1997. The TR89 closed out the series in 1999. New Holland's European division took a different route with the twin-flow machines from 1983, and the two design philosophies eventually merged into the CR line. Today, more than 70,000 twin-rotor combines have been built, and the current flagship models still use the same fundamental architecture that Machine introduced in 1975. That is a 50-year-old design decision that never needed reversing, and yet ask most people which combine broke the straw walker monopoly, and they'll name the wrong one. Number 5. Gleaner N6. Everyone who went rotary in the late 70s went axial. Rotors pointing front to back. crop traveling the length of the machine. Gleaner turned the rotor sideways, and 30 years later, they were still right. The N series was announced in February 1979, starting with the N6, built at Independence, Missouri. The smaller N5 followed within months, and a larger N7 arrived later the same year. The system was called Natural Flow, and the logic behind that name is the cleverest thing on this entire list. Think about the crop path in a conventional combine. The header cuts a wide, thin ribbon of crop. The auger squeezes it into a narrow feeder house. The feeder house feeds a rotor. The rotor spreads it out again. Every one of those transitions is a place where material bunches, slugs, and eats horsepower. The Gleaner transverse rotor sits crossways in the machine, the same orientation as the header and the feeder house. So the crop mat never has to be gathered up and redistributed. It enters as a ribbon and stays a ribbon, threshed around the full circumference of the rotor in a single pass. Under it sat the second good idea: accelerator rolls. Rather than letting threshed grain drift down onto the sieves, the rolls flung it downward at speed through a blast of air from a transverse fan. So a large share of the chaff was stripped away before the material ever touched the shoe, pre-cleaning in mid-air. It also meant the machine handled sloping ground better than most, because grain was being driven where it needed to go rather than sliding to the low side. The consequences were exactly what the industry now spends fortunes chasing: a short crop path, less power consumed per bushel harvested, less straw damage, and a light machine that didn't need to weigh 20 tons to do the work. And here's the proof: it was right. The transverse rotor didn't die with Alice Chalmers. It survived the Deutz Alice years, survived the move to AGSCO in 1990, and is still the defining feature of Gleaner combines. Refined into the solid core CDF rotor from 2006, but architecturally the same machine that appeared in 1979. A design that has run essentially unchanged for 4.5 decades in a fiercely competitive market is not a curiosity. It's a machine that got the answer right first time, and then had to wait for everyone else to care about fuel burn and soil compaction. Number 4. Claas Dominator CS and Commandor CS. Rubber tracks on combines are, as far as most farmers are concerned, a modern thing. Something that arrived with the big machines of the last 20 years to spread the weight of enormous headers and stop the soil being destroyed. Claas was delivering them in 1987. The story starts in 1981 with the Dominator CS. CS stood for cylinder separation, and it was Claas's answer to the straw walker capacity ceiling. Instead of walkers, or instead of American-style axial rotors, Claas fitted a bank of 8 transverse separating cylinders behind the threshing drum. The crop passed across them in sequence, and each one shook and beat more grain out of the straw before handing it to the next. It was a very European solution to a very European problem. Damp, tough, long straw doesn't behave in an axial rotor the way dry prairie wheat does, and operators who ran these machines will tell you the CS system could keep going in high-volume, tough conditions that stopped other combines. The trade-off was mechanical complexity, a lot of moving parts, and a repair bill to match if you neglected them. In 1986, the range was rebadged Commandor CS, and Claas pushed it into the giant class. The top model, the 228 CS, ran a 10-cylinder Mercedes-Benz engine of around 330 horsepower and could take cutting widths up to 7.5 meters. For the first time, a European manufacturer was going head-to-head with the biggest American machines on capacity. Then, in 1987, came the detail that makes this machine belong on this list. The CS combines became available with rubber tracks. Think about the timeline. Rubber-tracked agricultural machinery was barely off the drawing board. The first rubber-tracked farm tractor had been shown only the year before. Claas were putting tracks under a flagship combine in 1987, for the same reason everyone fits them now. As headers got wider and machines got heavier, tires were compacting soil in a way that cost yield the following season. The market wasn't ready. Tracked Commandos were built in genuinely small numbers, and Claas itself describes those series as low-volume machines that nevertheless shaped everything that came after. It took until 1997 and 1998 and the Lexion before factory-fitted rubber tracks on a large combine became a mainstream production reality under the TerraTrack name, and only in the last decade has the wider industry accepted tracks as normal, 10 years early, and forgotten because of it. Number 3. The Shelbourne Reynolds Stripper Header. This one isn't a whole combine. It's a front end, and it questions something nobody had questioned for a century. Why are you cutting the straw at all? You want the grain. The straw is a passenger. Yet a conventional combine cuts the entire plant, drags the whole mass through the feeder house, threshes it, separates it, cleans it, and throws the straw out the back, burning fuel and capacity on material you were going to leave in the field anyway. In 1985, Keith Shelbourne of Shelbourne Reynolds in Suffolk proposed a different approach, adapted from the rotor head on the company's own pea harvester, which stripped peas rather than cutting the plant. Instead of a knife, you fit a rotor carrying rows of shaped stripping fingers that comb through the standing crop at speed, tear the grain heads off, and leave the straw standing in the field. Shelbourne took the idea to the Silso Research Institute, the UK's National Agricultural Engineering Research Centre, and the response was enthusiastic enough that stripper header development became a priority project. Silso engineers published on it through 1986 and 1987. Shelbourne Reynolds took the manufacturing and marketing rights. Production began in 1988, and it reached the UK market in 1989. The results were extraordinary. Because so little material entered the machine, combined output rose by 50 to 100% depending on the crop, while power requirement fell. The highest reported output for a stripper-equipped combine in rice in Australia was 59.6 tons per hour. And then British farming did the one thing that could kill it. The stripper leaves a field full of tall standing straw. In 1988 that was fine because you burned it. In 1989, the UK phased in a ban on straw burning, and suddenly every stripper owner had a field of standing stubble they had no way to deal with. Domestic interest collapsed almost overnight. The technology survived by emigrating. American no-till farmers realized that standing stubble was not a problem but a feature. It catches snow, holds moisture, shades the soil, resists erosion, and leaves clean ground to drill a second crop straight into. Shelbourne Reynolds launched the CX range in 1995, aimed squarely at U.S. prairie wheat growers, with the 28-foot CX-84 becoming the popular model. Stripper fronts found homes in rice in Australia and Italy, in Russia, and in kit form in China. It has real limits. Front-end losses run about 1% higher than a cutter bar. It struggles in thin or large crops, and it can't handle oilseed rape. But as an idea, stop harvesting the part you don't want is more relevant now in an era of conservation agriculture and controlled traffic farming than it was in 1989. Number 2. John Deere CTS. By the early 1990s, the combine world had split into two religions. Conventional machines used a transverse drum and concave, then straw walkers. Gentle on the sample, kind to the straw, brilliant in tough European conditions, but capacity limited because walkers can only be so long. Rotary machines used a rotor for everything. Huge capacity, superb in dry crops, but harder on straw, and unhappy in damp, tough, high-moisture material. Deere asked the obvious question that nobody had productionized. Why not both? The CTS cylinder tine separator launched in 1992, and Deere describes it as the world's first hybrid combine. The front half is conventional and deliberately so, a 26-inch diameter threshing cylinder with 14 rasp bars and a long 116-degree concave wrap, which threshes gently and produces a clean, unbroken sample. Then, where the straw walkers should be, there are two counter-rotating tine separators that take the material forward and shake out the residual grain by rotary action rather than by gravity. The result was a machine with the sample quality of a conventional and much of the separating capacity of a rotary, in a body no wider than a walker machine. Owners describe it as having enormous capacity for its physical size, a 5-walker footprint doing 6-walker work, and it earned a particular reputation in tough, damp, high-residue crops and in rice, exactly where pure rotaries of the day struggled. It also had a rough ride commercially. It arrived in Europe late. The UK debut was 1998, and was succeeded there in 2001 by the 9780 CTS, built at Zweibrücken in Germany, with 310 horsepower, a 10,000-liter grain tank, automatic header float, and molded composite side panels. Deere never built a wide-body version, which many operators regard as the great missed opportunity of the whole line. It had its weak points too, including a modest sieve area that could be overwhelmed and bearings that punished neglect. But look at what happened next. Claas launched its APS hybrid Lexion in 1995. New Holland went hybrid. When Deere's patent protection expired, hybrid layouts spread across the industry. And today the hybrid combine, conventional threshing, rotary separation, is one of the two dominant architectures on Earth. The machine that started it is now cheap used iron, bought by farmers who want serious output on a budget and almost never mentioned when people list the important combines of the 20th century. Number 1. Massey Ferguson MF30 and 40 series with Datavision. And here's number 1, a combine that was ahead of its time, not because of anything mechanical, but because of what it was quietly doing while it worked. It was making a map. By the late 1980s, one thing had become obvious to anybody who thought carefully about fields. A field is not one thing, it's a mosaic. Different soils, drainage, compaction, pH, exposure, and yields inside a single field can vary by a factor of 2 or more. Farmers knew this. They just had no way to measure it, so everything got treated the same, everywhere, forever. The reason it had never been measured is that a field only tells you its yield at one moment, the moment it's harvested, and the only machine present is the combine. Massey Ferguson got there first. Their in-cab interactive information display, Datavision, originally known as Datavision, was already the first of its kind. Then, in 1991, Massey Ferguson introduced the first yield mapping system offered on production combines, using a grain yield meter, the Datavision display, and GPS satellite positioning. Fitted to the MF30 and 40 series combines, it recorded how much grain was flowing through the machine and where in the field the machine was standing when it flowed. Drive a field, and it drew you a yield map. Everything we now call precision agriculture starts there. Variable rate fertilizer, variable rate seeding, management zones, prescription maps, the entire farm data industry, every yield layer in every farm software package, all of it descends from combines quietly logging bushels against coordinates. There were pioneers around it, and they deserve naming. In 1988, a Yorkshire farmer, John Fenton, was already running a Massey Ferguson M38, fitted with a gamma-ray yield sensor on his own farm. In the US, AgLeader released the Yield Monitor 2000 in 1992, the first genuinely accurate combine yield monitor, and it became the backbone of American precision farming. And the technology was hobbled by something entirely outside agriculture. Civilian GPS at the time was deliberately degraded by the US military under a policy called selective availability, which introduced positioning errors of up to about 100 meters. Farmers were mapping variation inside a field using a signal that couldn't reliably tell them which part of the field they were in. Selective availability wasn't switched off until the year 2000, so the first yield mapping combines were doing something genuinely revolutionary with one hand tied behind their back, and their operators mostly used the data to stare at a printout and think, well, that's interesting, because nothing existed yet to act on it. Those machines are now 25-pound-an-hour used combines. The idea inside them became a multi-billion-dollar industry.